We have seen what is IPv4 protocol packet structure, and we have learned the IPv4 protocol by making use of Wireshark. And let's see a UDP protocol in this session. And take a download sample captures from here. I can download the I can use we can start to capture conversely right from here. Sorry, for that first you need to select the interface Wi-Fi. Okay, they start to capture, so you can capture, but you see here is the I'm using what IPv4. It doesn't matter if it is IPv4 or sorry, here it is IPv6. IPv6 address is what actually assigned to the interface, my network interface controller, a card, and this communication is happening between the IPv6. But it doesn't matter regardless of what protocol in the network layer we are using, whether that can be IPv6 or IPv4. It doesn't matter, but it doesn't matter when it comes to the transport, right? So transport layer, the protocol that is in the transport layer, that can be UDP or TCP, that works independent or regardless of the network layer or internet layer protocol, IP protocol, that can be IPv4 or IP6. And we will learn about IPv6 in detail and IPv6 address, but let's focus on UDP protocol. So what is UDP protocol? In a TCP IP suite, suite, there are a set of protocols. So these are a different set of protocols in a TCP IP suite. Such as we have in transport layer, widely there are DCCP, SCTP, and we don't use that, that are not widely used, and you won't you will hardly hear about other protocols, but widely used transport protocols are UDP and TCP. And in a network layer, internet layer, these are different protocols. What are IPv4, IPv6, ICMP, IPsec, BGP. Okay, so and we have learned, we have seen the IPv6 protocol, sorry, IPv4 protocol, and let's see UDP protocol. So I have captured what is UDP protocol. Click on this one. So what is the packet structure of UDP protocol? See, here is the one. This UDP protocol is described in this wiki, along with the encapsulation that along with the IPv4 and the IPv6. You can see here the UDP datagram header. So UDP packet is very simple. Packet structure or format, which is very simple, that is fixed of 8 bytes. It contains only 2 watts. Okay, so that is fixed, unlike IPv4. It is fixed. It contains always a pixel length of 8 bits. Source port, destination port, source length, length, and checksum. Remember, this checksum is optional in IPv4, but it is a mandatory when it comes to IPv6. UDP checksum is mandatory in IPv6. So this is UDP header followed by the data. This data comes from where? This data comes from the upper layer, right? And upper layer data is encapsulated. Upper layer data is encapsulated into the lower layer, that is from the application layer. The data is encapsulated into the UDP packet here. Okay, you can see here, as you can see, can you see it is better shown here? You can see you have IPv4 packet and IPv4 packet is having header, and IPv4 packet data or a payload or a body, and that body contains the encapsulated UDP segment. And you see UDP is having again, again UDP is having header and body, and this body is a what is the application layer protocol. That can be a pure data or a protocol from application layer. See, this UDP segment is encapsulated into IPv4 packet. IPv4 packet, that it is having header, and this whole segment is encapsulated into the IP packet as a body or a payload. Any questions? Yeah. So you can see total these bits are numbered, and this is the leftmost bit and rightmost bit, and it is a most significant bit and least significant bit. Okay. So here the how many watts you have here? This is 1 byte, 2 byte, 3 byte, 4 bytes. 4 bytes, or it is a 4 byte watt. Total 2 bytes, or in the sense 8 bytes. So UDP packet is of total size 8 bytes. Got it? Okay. So when it comes to as you scroll down, if you take the IPv4, it's a pseudo header format. It means that to demonstrate how this is encapsulated, here IPv4 header format is taken, and you have the IPv4 header that has a that is a source header, source address, destination address. Okay, this and IPv4 is having options under padding. Okay, that we discuss, and after that, see, this is not here. It is not described properly in that same order, but you see this IPv4 UDP packet is encapsulated here, and followed by the IP header. You have the UDP packet source port, destination port, length, checksum, data, and the same when it comes to the IPv6. And so we have captured some data for a UDP. And what protocols use the UDP? UDP is used for the time sensitive communications, such as where speed matters. Okay, what is the difference? There are different protocols in a transport layer. As you can see here, what are the protocols in transport layer? We have a TCP and UDP. But why how do we choose which transport layer protocol to use, whether TCP or whether UDP? It is used depends on the reliability versus speed. So which protocol is reliable? TCP protocol is reliable, but UDP is not reliable as much as TCP, but UDP is faster than TCP. Why? Because there is no flow control and error detection or error checking mechanism. Flow control, congestion control, error detection, correction, and sequencing. These are all things are available in TCP, but those are not available in UDP. UDP is like leave it out there. Okay, so there is a see, this is like better explained with this kind of meme here. You see, TCP is like this. There's a flow control, okay? So TCP checks whether connection established or not, and TCP checks whether that data that one from one end. You see, you see here, it is UDP, it is TCP. If computer is sending request to server, TCP, that protocol, there is a mechanism in that protocol. It checks whether data is reached other end or not. If it is not reached, that will be retransmitted. and there is error that is discarded, and so there is a mechanism for a flow control, error detection, congestion control, and correction mechanisms are there. But this is like a UDP. It is just a leave it out there. Leave it out there whether it is a best effort. Okay, the UDP protocol, any software or hardware that sends packets through UDP, thinks that assumes that with the best effort packets will be reached the other end, will be reached the other end. Yes, yes, yes. This is also better explained. Yeah, TCP, UDP. This is SSH and this is VPN. Yeah. Okay, this is P2P and broadcast. This is broadcast and this is kind of multicast. Remember, multicast. There are actually unicast, multicast, and broadcast. These are our IP communications. Multicast. There are multicast addresses. Remember, uh, get80.com. Their multicast addresses are out there for IPv4 address. You see, class 1, class E. See, multicast address, that class D is reserved for. All these addresses are for multicast. Any computer that joins or gets this IP assigned will join the multicast. So they are like in the same group. So they anything that is sent to the any of IP, any one of the IP that multiple systems are using or listening at on the multicast, so they all receive the packet. So anyway, and there are so that is a difference between TCP, UDP, and okay. So yeah, you see, this is like a TCP, UDP. So this is best best explained. So that is a reliability. This whole thing I'm explaining. Yeah, that is the thing. See, TCP is reliable, but UDP is not reliable as much as TCP, but very faster than faster than TCP. UDP is faster than TCP. Why? Why? Because see, there is no error control, so it is like uh, with the best approach, anything that is sent out there will be reached the other end. But by using UDP, upper layer protocols tend to implement the error detection and correction mechanisms, upper layer protocols. So there is a lot of overhead when it comes to the TCP. What is the overhead? See, here, look at this. Look at this TCP. We will learn the TCP uh, in detail, but we will use it. But for the time being, check. To establish a connection for a TCP, there must be a three-way handshake where a client should send the synchronize and server should send a synchronize acknowledge, and client will send a acknowledge. Then only connection will form. Connection will be established. So every time connection is formed, what happens? There is so much overhead here, right? There's a see on top of data, then after this three-way handshake only your data will be sent. Okay, so there is a overhead of this three-way handshake, and there is a complex, so much complex. Let me tell you, let me show you the difference between TCP header and UDP header. Okay, look at this TCP header. See, can you see this TCP header? This is a source port, sequence number, acknowledgement, window, urgent, checksum, pointer, offset, okay, options. So much is going on here. Can you see? So much is going on. So complex it is. But look at the UDP. That is very simple. Okay. This is a TCP header. Okay, so And here also we have optional, which is 20 bytes, and you can have options. Okay, so this is complex, as complex as IPv4 header, and even complex than IPv4. You have window checksum, and there's a flow control. Okay, but anyway, we'll discuss that is for the others. In we can dig deep into the TCP, but can you see this? There is a overhead when it comes to the TCP. There's a overhead of a connection establishment and connection tear down. So there is a when connection needs to be closed. Okay, so let me show you one thing here. We can do with the Wireshark. We can do one thing here. I'm looking at the TCP. Let me search if there is a TCP. Yes, we have the TCP. And see, I filtered everything by TCP. And you can go to the menu statistics, and you can go to flow graph, and it will show you everything. But I have filtered that by TCP. So if you select the limit to display filter, you will see only TCP. Can you see here? Can you see here that connection establishment? Okay, we haven't captured the complete one. So let me do one thing. Let me open a recent file. Okay, it has a TCP. Okay, so let me go here, filter this TCP, take the first packet, take any TCP, right click, follow TCP string. So you will see everything, every data. If you click on follow TCP stream, you will see everything, the all data that was communicated through the TCP protocol. And now you can see here that TCP filtered, particularly the TCP string. What I can do now, I can go to statistics. And go to flow graph. And now limit by display filter. Okay, can you see here that this is all these things are connection establishment. This is called a three-way handshake. Client sent the synchronize, and this you might be confused. What is synchronize? What is acknowledgement? What is synac? Okay, for the time being, leave it. We'll discuss about those flags. But after that only, you can see here the data flow started. And but when it comes to the connection tear down, when connection can't be closed abruptly, so if we to close this gracefully, client or server will ask for the finish, and then server will send fin acknowledge, and then client will send acknowledgement. So three-way handshake. There is also three-way handshake for the tear down. So it's like you meet some person, but before you talk, you say hello, you you shake his hand 3 times and then say hello. Okay, and then if you leave it, before you leave, after you talk everything, before you leave, shake your hands twice and leave. It's like that. So you are actually putting lot of effort in shaking hands like this. There's a lot of effort in making a connection. So, but there is a reliability here. Reliability comes with this three-way handshake that time it is taking, because as it is connected, data flows through this, and for every packet, TCP takes care of whether that packet is reached the other end. If it is not reached, that will be retransmitted. But that is like a TCP. But when it comes to UDP, so there is no shaking hands. So you don't when you want to say hello to someone, you don't have to see. For in a TCP, to send some information, it has to wait until three-way handshake is done. But a UDP, you don't have to wait. Like you in a party, you meet someone, you don't have to wait until you shake his hand twice to say hello. You can just shout hello, hi, hello, how are you? So which is kind of fast, isn't it? But that is not reliable. Let's say you are actually far away and you are saying hello, and thinking that he listened to your voice. Okay, with the best of what you are thinking, he heard about he heard your voice. But you see, but that is quite fast. You want to say something, you want to tell something, that is quite fast. You don't have to wait. So that is a thing. This is a thing when choosing a correct transport protocol, whether to choose TCP or whether to UDP. Okay, so TCP protocol is used when reliability is at most important. UDP protocol is chosen when reliability is not more than reliability. Time matters the most. Means it has to be more fast. So what are the cases where the UDP used? UDP is used where UDP is used for a DNS protocol, for a VoIP protocol, and RTP, real-time transport protocol, and trivial file transfer protocol. That is TFTP. Okay, so in this kind of protocols, UDP used. Why VoIP is for a VoIP protocols? VoIP means I'm talking with you on a phone, Skype, or Google Meet. So why in those cases why UDP is used? Because connecting over TCP might be delay. In such a case, even it is a kind of split second. You will hear my voice even with the on by adding even some latency. You will hear my voice after a couple of seconds. It is like you will hear some kind of delay, which might be annoying, right? After I say hello, you listen to that after a couple of seconds. How does it feel? Yeah, lagging. So, and even in a gaming also UDP is used, because if you are playing a game, you want to, if you are playing multiplayer online gaming, you don't want to experience a delay about see, if you are playing a first person shooter game, and you don't want to see that with the lag, if your friendly neighbor is actually lifting a gun and he's shooting you, and if you see that after a couple of seconds, you are already dead. Okay, so in those cases we need a UDP. But what about, you might ask a question, okay, we are considering a real speed. We want speed over reliability. What about if there is an issue over the network, there is a packet loss? That packet loss error correction detection mechanism is not taken care of UDP. That is taken care by, that is delegated to the upper layers. If want, upper layers take care of retransmission and error checking, if upper layers do really want that. Okay, otherwise in those cases those packets are retransmitted. But in sometimes, couple of packets that are lost doesn't make any difference if you are talking over phone. See, I'm talking you on a phone. RTP is based on UDP. Okay, RTP is a protocol, which is a voice real-time transmission. Hello. Transmission protocol that protocol carries the data, critical voice data, RTP. Yeah, real-time transport protocol. Okay, so what it carries, delivering audio and video over the IP networks. Can you see? Okay, so this is on top of UDP. So you may tell, if I'm talking to you, if couple of bits or couple of packets are lost, you won't lose whole word that I spoke. There might be some glitch or something, but you won't even notice for the couple of packets that are lost. Okay, do you get it? Okay, so there has to be a lot data loss of that is depends on networks. Couple of if there are a couple of packets, it doesn't cost much. Okay, but for a watts to loss, they lot of because samples are sent over this, the multiple samples. Uh, so multiple packets needs to be, need not to be delivered for the whole world, or uh, you know to last couple of watts or so, like that. So it typically runs on UDP. Okay. So anyway, like that, there are different protocols: DNS, UDP, and DNS. Why DNS is on top of UDP? DNS. Why DNS is used? DNS is used to translate domain name. What is this? This is wikipedia.org, and DNS is used for this to convert to translate this domain name to the IP address. Okay, this domain name to the IP address. So this domain name to IP address to translate, we use DNS. But tell me, see, you are actually, I'm going to this website, going to new website, and I type google.com. Okay, and go to the inspect. There you can see, go to the network, and there you can see what's going on here. So you can see the time for this whole page to be loaded. No time it took that this whole page to load. Know how much time each. Lot of things are loaded here, from the document to the images to the scripts, and you can see the total time. Some are some are getting loaded from this cache, though they are taking as much as 1 millisecond. Some are taking 300 milliseconds. 500 milliseconds means a split second. Half second. Okay, so in such a case, there is also one more thing here. Right click, click on domain, and this is google.com. Right click, click on protocol. You can see which is a protocol, H3, and remote address. What is this remote address? Which is IPv6 address. Okay, can you see IPv6 address? So here in this IPv6 address, how come this browser know about IPv6 address? DNS. Okay, domain. So and let's say that for this website to see, if I refresh, how much time it is taking. It is not even taking much time. You want the website to work like that, right? You don't want website to take a couple of seconds even, because people are short tempered that they just leave the website if it is taking just 2 seconds to load. So they want this websites to load just within 1 second. But there's a network latency here. Network latency. If I check the waterfall, this waterfall, you can see here time for each duration. Can you go google.com? Let me refresh this. Reload. This is the waterfall. It describes how much each 372 milliseconds, right? Okay. So in that you can check the duration for what each call, how it is actually taking. So do you see here the DNS? I have to reload a full reload without catch. Now I check. Can you see here DNS lookup? How much time it took? Yes. And we will add here, of course, why it took this much time for the DNS look. This might be actually, you might have got this DNS query answered from the cache of one of the resolver in the middle, from the gateway. Routers sometimes catch the lookups, recent queries. So they invalidate the catch after some time, and then if DNS request came after that time, after that much time, they actually reload, invalidate the catch, and query that DNS to the other root DNS servers or other servers, authoritative servers. So in such a take, it might take time. But assuming it is taking this much time, but let's say that assuming it might not take 20 seconds, but it might take a 300 milliseconds or like that. If it is not from the catch, assume. Okay. So in such a case, tell me, or let's say, just assume. Let's assume 200 milliseconds it takes with the UDP. This is, this much time here, 24 milliseconds, which means very, very last. You can't even measure. Okay, very, very less. So that is possible because it is on top of UDP. Let's say that, your protocol is also TCP and UDP, DNS is also over TCP. So if DNS query is taking half second and your page is taking half second, you will wait 1 second. So you want this thing to be, DNS is critical, and it has to be used by all of for every domain to be resolved, used by browser or any application. They use DNS. In such a case, it needs to be faster. So let's say if there is a packet loss, what happens if that domain query is not answered and you haven't received the response? In such a case, what happens? These applications can afford to make another DNS query. Okay, do you get it? So this DNS is a query on top of this DNS is a protocol on top of UDP, such that it can be fast. And what about reliability? This is just a domain name, your IP address. This is not reliable. You want fast, you want a speed more than reliability. If packets are corrupted, of course you can make another DNS query in a couple of milliseconds, after in a few milliseconds, by checking. That is not an issue. Now, do you understand where DNS is required, where UDP is required, and where TCP is required? UDP is used when it comes to the timing, and so TCP is used when it comes to the reliability. No, it is a mixed. This HTTP protocol is on top of TCP. Okay, file transfer protocol is on top of TCP. Okay, when you are transferring file, you need that reliability. You want to download each bit. You are downloading, let's say you are downloading a OS and a few bits are missing. What happens? You can't properly install that operating system if they are critical. Yeah. So that is the case. Now let's go back to our learning. DNS, if you take a DNS query, can you see here? And here is the UDP protocol, and it has a source port. Select everything and you can see the UDP header. How many bytes UDP header is? 8 bytes. Can you see that here clearly? Okay. So 8 bytes. So you can clearly also see those bytes here highlighted right side. 1, 2, 3, 4, 5, 6, 7, 8, right? And in those 8 bytes, first 2 bytes are for a port number. So port number is like a window for a transport protocols. Port number is used to identify the application that made this network request when response is received. Okay, so any application that is making a network request or reasoning over the network socket, they are bound to the specific port, whether it is a TCP or UDP, such that those applications are identified based on the port. think of port as a window for application. So these port numbers are like IP address in the network layer, that is address to identify host. Port number is used to identify the applications, apps or applications or a software or a process. Okay, so if you have opened Instagram, that Instagram creates asks the request, opens the network connection and downloads the photos. But to download photos, when that network data came back to your phone as some bits and pieces, those photos needs to be that operating system, that iOS or Android, that needs to process, and that data should go through the decapsulation, and that should be given to the proper application, that is Instagram. In such a case, how when it is actually there at the IP layer, encapsulation and decapsulation here, let's say, so here uh, bytes are received and they are destined for the Instagram. So data link layer removes the frame, and as it is a de-encapsulation or decapsulation, network layer removes the network packet header, IP header, and given to the transport. What transport does? Transport looks into the segment header. Okay, segment header. So segment, it is PDU. What PDU is called in a transport layer? It is called a segment. So that can be either TCP or UDP. So in a segment header, it checks the port. What port it is? Let's say here in our case, what port? This is source port, which is a 2719. So what it does, let's say it is destined to 2719. It checks that port and gives to the operating system. Operating system process that and finds out which application opened a socket with that port, and finds that application. That application would be the Instagram. Okay, and Instagram, and the data will be given to the Instagram. The what would be the data there? Photos, images, and Instagram takes those images and sends, displays them. Okay, so let me show you one example here. If I take a, let me take a new window, let me show you. Can you see here? You can see addresses. Local means the system address, and foreign means to which address it is communicating. Okay, and here you can see the TCP or IP. Okay, and here you can see. Let me show you. We can display. So there is also a command lsof -. Can you see here each process is assigned with a IP process ID. Okay, you can see here the PID and command. You can see this protocol, see UDP or TCP. And for suppose there is a one syslog D that is listening over the protocol 56719, And what is the PID of that? 71. Process ID. Do you understand this? These port numbers are bound to the processes or apps. Got it? See, there is a google.com. There's probably the browser and the UDP. And what is that browser tab? That port, which is a 64729, and it is associated with that particular browser tab. Do you get it? Hello, do you get it? Any confusion? Okay. So this is about UDP. You have the source port and destination port, and which is also 16 bits, and the length, which is the length of the packet. Can you see here DNS query how much it is? 33 bytes. So which is 33. And what is the 8? Tell me 33 plus the 8, how much it is? 41, isn't it? Okay, you can see this is the total length. Total length means see 8 bytes are for a header and 33 for a body. Okay, so and you have the total DNS 33 bytes, which is a data that is which is a payload of which is a payload. You can see the UDP payload, which is 33 bytes here in status bar, and if you select the DNS query, which is also 23 bytes. So this DNS query, which is a DNS protocol of the application layer, encapsulated to the UDP layer, transport layer, and placed into the payload of the UDP. And UDP is placed into the payload of the or data of the IP. And you can see that is a thing. What about this checksum? Checksum is not mandatory, but used. Where is checksum for the UDP here? Yeah, checksum. Here is the checksum. This checksum is also 16 bits, which is calculated. A calculator where it actually when source source computer is sending a data, it calculates the checksum of the packet and puts that into the checksum field of the header. So receiving party can take this checksum and verify the packet received, and the receiving computer or a server calculates the checksum for the whole packet and compares with the checksum in the checksum field. If both are same, packet is not corrupted. If both are not same, packet is said to be corrupted. In such a case, the packet will be dropped. But this IPv4, that is optional, but it is mandatory in IPv6. This is simple protocol in a UDP, and you can see the query, and you can see you can compare the UDP. You can filter UDP using UDP. Just typing UDP in a display filter, and you right click and you can flow UDP stream. In such a case, you can see what was the stuff that was communicated over the UDP. You can see that in ASCII.